Hydrogen bonds and the special properties of water. As you can see by the title, we'll be talking about the special properties of water. 4 special properties to be exact, without which life as we know it would not be possible. Let's start with something we know. Water is a very polar molecule. Oxygen is more electronegative than hydrogen, which means electrons spend more time with oxygen than with hydrogen, resulting in a polar covalent bond. Each hydrogen has a partial positive charge, and the oxygen has a partial negative charge. As you can see from this diagram, the oxygen atom has 2 centers of negative charge. Here are 2 more ways to look at it. Water is the V-shaped molecule with oxygen at the vortex and hydrogen at the ends. Delta positive, as opposed to just a positive sign, means partial positive charge. Likewise, delta negative means a partial negative charge. Sometimes a water molecule is written just as an inverted V, and you should know where the oxygen and hydrogens are. Polar molecules like water can form hydrogen bonds, which I'll generally just call H-bonds. In water, an H-bond forms between a partially negative oxygen of one water molecule and a partially positive hydrogen of another water molecule. So water has both intramolecular polar covalent bonds and intermolecular H-bonds. As the diagram shows, each water molecule can associate with 4 other water molecules because there are 2 centers of positive charge and 2 centers of negative charge. Unlike the polar covalent bonds that hold water molecules together, the H-bonds between the water molecules are not fixed. They break and reform all the time. While water is a good example of H-bonds, the best example really, there are lots of situations where H-bonds will form. Generally, we can define a hydrogen bond as an electrostatic interaction between a partially positive charged hydrogen atom in one molecule and a partially electronegative atom of another molecule, usually oxygen, nitrogen, or chlorine. That's what H-bonds are, but why are they important? H-bonds are relatively weak, weaker even than ionic bonds. When we talk about the strength of a chemical bond, we mean how much energy is required to break them. Here we see that covalent bonds are strong and don't break easily. Covalent bonds, in other words, are relatively fixed. They don't change. We've already seen that ionic bonds are much weaker and can break when an ionic compound, like sodium chloride, is dissolved in water. H-bonds are weaker still. This makes H-bonds reversible. That is, they form, break, and reform all the time. Weak reversible bonds are very important in biology. As we'll see in a moment, H-bonds give water its special properties, without which life on Earth would be impossible. But H-bonds are also important in other molecules. Here are 2 important ones, DNA and protein. We've already looked briefly at the structure of DNA, and we'll examine it in great detail later in the semester. For now, however, let me just repeat that DNA is a double helix. Each of the tan ribbons represents one strand of the double helix. Critical to the passage of information from generation to generation is the ability of these 2 strands to come apart as part of DNA replication. The strands can come apart because they are held together by H-bonds, which are reversible. DNA molecules come apart, get replicated, come apart again, and get replicated again, and on it goes for generations, ensuring the accurate passage of information, all because of reversible H-bonds. Proteins we haven't really talked about, but we'll explore them fully a little later in the semester. As we'll learn, proteins have many functions, and these functions depend critically on their 3-dimensional structure. Covalent bonds are part of the backbone of protein structure. Here, individual subunits of proteins are shown as circles, and these circles are held together by covalent bonds. This string, however, folds back on itself to form a 3-dimensional structure, and this 3D structure depends on H-bonds. Once again, these H-bonds are reversible, and a protein can lose its 3-dimensional structure. In that case, we say the protein is denatured. When that happens, the protein is no longer functional. Okay, back to water. I'll go over each of these special properties in turn, but for now, let me just list them. Water is very effective at moderating temperature. That is, water resists changes in temperature. Water is also a sticky molecule. It sticks to itself, that's called cohesion, and it sticks to certain other molecules, that's adhesion. Water is the solvent of life, meaning many of the molecules needed to sustain life are readily soluble in water. Water also has the unusual property of being denser as a liquid than as a solid. This means that ice floats. As we're talking about each of these properties, keep in mind that they all derive from water's unique ability to form H-bonds. And because of these special properties, water makes life possible. When we say that water promotes temperature moderation, we mean that water resists changes in temperatures, or it takes a lot of energy to change the temperature of water even a little. There are several reasons why this is the case. I will discuss only two of them: heat capacity and transition energy. Keep in mind that they all depend on water's ability to form an extensive network of hydrogen bonds. Water has a high heat capacity, meaning that it takes a lot of energy to raise the temperature of water. Heat capacity is defined as the amount of energy necessary to raise the temperature of 1 gram of a compound by 1 degree Celsius. For water, that number is 1 calorie, and that is high compared to many other liquids. The international unit of energy is the joule, and 1 calorie equals 4.2 joules. Now, let's delve deeper into the structure of water and see why water has these properties. If you get it, great. If not, then just remember the basics. Let's start with a water molecule, with its oxygen, which has a partial negative charge, and its two hydrogens, which each have a partial positive charge. As we'll learn later in the semester, water and all molecules are in constant random motion, called Brownian motion. In other words, the molecules have kinetic energy. Kinetic energy is the energy of motion, and we measure kinetic energy as temperature. Temperature equals kinetic energy. When we say that the temperature of water is high, that means that the molecules have a lot of kinetic energy and are moving quite quickly. Or, as we add heat to water, we raise its temperature and increase the kinetic energy of the molecules. Here's where water's high heat capacity comes into play. Remember that water forms H-bonds, lots of H-bonds with neighboring water molecules. Here is an H-bond between the oxygen of one water molecule and the hydrogen of another, and so on. Remember also that these molecules are in constant random motion, and the faster that motion, the higher the temperature, or kinetic energy. Because of all these H-bonds, the movements of these water molecules is constrained, and they're not necessarily free to move faster. In other words, before you can increase the kinetic energy, temperature of the water molecules, you have to break a lot of hydrogen bonds, and that takes a lot of energy. Another aspect of the temperature moderating effects of water is transition energy, or evaporative cooling. Essentially, whenever water evaporates, it has a cooling effect. To understand this effect, let's consider a beaker of water. As usual, we have to consider the water at a molecular level, and I've drawn in water molecules interacting with one another. Remember that each water molecule can interact with 4 other water molecules. Water molecules interact with each other in the solid or liquid state, the so-called condensed states. That's more or less what defines a solid or liquid, the degree of interaction of the molecules. In the gas state, individual molecules are on their own, not interacting with one another. Let's consider a water molecule passing from the liquid to the gas phase. Here we have a water molecule in the liquid state, and it is constrained by all the H-bonds it forms with other water molecules. In the gas phase, it's not H-bonded to other molecules. In other words, to enter the gas phase, each molecule must break all the H-bonds it has with other molecules. This, of course, takes energy. Lots of energy. 540 calories per gram. The energy absorbed by water as it enters the gas phase escapes. The liquid left behind, therefore, has less energy, or it's cooler. In other words, evaporation is a cooling process, hence the term evaporative cooling. Evaporation happens at the surface of a liquid because the molecules there are least constrained by H bonds and require the least energy to pass into the gas phase. This is the basis of measuring the relative humidity with a wet bulb hygrometer. It's also the way our bodies cool themselves. When you get hot, you sweat, which is the secretion of water to the surface of the skin. That water evaporates and cools the body. It's more difficult to stay cool on humid days because the sweat doesn't evaporate as quickly. Of course, your body resists changes in temperature in the first place because you, like most organisms, contain a lot of water. The other phase transition, ice to liquid water and vice versa, melting and freezing respectively, also absorbs or releases a lot of energy, 80 calories per gram. We know that adding ice to hot liquids will cool them off quickly. That's because it takes a lot of energy to melt that ice. Like biological systems, we also take advantage of water's ability to absorb a lot of heat. That's why we use water to cool the engines in our cars, and even to cool nuclear power plants. The temperature moderating effects of water also affect climate, both locally and globally. The climate in San Diego is mild. It doesn't get too warm in the summer or too cold in the winter, because we live near a large body of water. Globally, the Earth's temperature stays within a narrow range because of all the water it contains. I'll talk more about that in a future video. Our next special property of water is actually two related properties, cohesion and adhesion, and we consider these both at once. Cohesion is the tendency of water molecules, or other kinds of molecules, to stick to each other. You know that water molecules stick to each other via H bonds. Cohesion gives rise to surface tension, which measures how difficult it is to break the surface. You've seen examples of surface tension many times. If you overfill a glass of water, you know that it can form a dome above the rim. That's due to surface tension. When water beads on wax paper or other hydrophobic surface, that's surface tension. In this example, surface tension allows a water bug to walk on water. Here, the force of the insect's legs on the water, its weight, is less than the cohesive forces holding the water molecules together, so the surface doesn't break. While cohesion is an attraction between water molecules, adhesion is attraction between water molecules and other types of molecules. For example, you see water beading on wax paper, but it will spread out on glass due to adhesion, an attractive force between water and glass, due to hydrogen bonds formed between water molecules and the molecules that make up glass. You also know that paper absorbs water. This is also due, in part, to adhesion. Substances that attract water are called hydrophilic, or water-loving. The properties of adhesion and cohesion combine to generate capillary action. Here is an example of capillary action. In a small glass tube, or capillary, water will defy gravity and rise. This represents the water level, and you can see that the water in the capillaries is above it. How do we explain capillary action in terms of cohesion and adhesion? The glass is a hydrophilic surface and water sticks to it, adhesion, to climb up the capillary. As the water rises, it brings more water with it, cohesion. Note that the smaller the capillary, the higher the water rises. That's because the opposing forces of gravity and capillary action are acting on the column of water. The water will rise until the weight of the water is equal to the forces of cohesion and adhesion causing the water to rise. In all cases, the weight of the water is the same. In a smaller capillary, that will mean a higher column. Capillary action is the basis of transpiration, the means by which plants, even very large trees, transport water from the ground to their uppermost leaves. Without it, plant life, and consequently animal life, on Earth would be very different. Sodium chloride, like many salts, is necessary for life, and like many of the things necessary for life, it dissolves in water. That's why we call water the solvent of life. Water dissolves more things than anything else we know of. To understand the powerful solvent capability of water, let's take a look at what happens when salt dissolves in water. This is set up so you can see a small band of undissolved salt in water. As you know, that salt will dissolve when you stir it up. That means that the solid salt, which is a crystal lattice held together by ionic bonds, breaks apart such that individual ions, positively charged sodium ions and negatively charged chloride ions, interact individually with water molecules. As we said earlier, ionic bonds are weak, so weak that they fall apart in water. Here you can see why. Each individual chloride ion, an anion because it's negatively charged, interacts with several water molecules via their partially positively charged hydrogen atoms. Likewise, each positively charged sodium ion, or cation, attracts several water molecules via their partial charges on oxygen. All told, the interactions between water and the sodium and chloride ions is stronger than the interactions between sodium and chloride for each other. That's why salt dissolves. Most ionic compounds like potassium chloride or sodium chloride, magnesium chloride or magnesium sulfate will dissolve in water. Importantly, amino acids, which are the building blocks of proteins, are ionic and they dissolve in water. Nucleotides are the building blocks of DNA and RNA, and they are also ionic and soluble in water. Sugar is not ionic, but it nonetheless is very soluble in water. We'll look closely at the structure of sugar in our next module, but for now, sugar, for example glucose, has many polar side groups which interact with water, which is also very polar. Like dissolves like is generally how we describe polar compounds like sugar dissolving in water. Lipids are a class of molecule that is patently not soluble in water, and we'll deal with them in the next module. Finally, we have the fourth special property of water. Water is less dense as a solid than as a liquid, which is a very unusual property. Most compounds are denser as a solid. Think of something heavy, like lead. Lead is very heavy and dense, but when you melt it, you wind up with a liquid that is less dense. You can take that molten lead and pour it on top of solid lead. Otherwise, we wouldn't be able to mold metals. Water is different. Its solid form, ice, is less dense than its liquid form. For the record, water is at its greatest density at 4 degrees Celsius, just above the freezing point. Why this is the case is a little hard to explain, but let's hold off on that and consider the implications of this fact for life. Ice floats. That's why you can skate on ponds or lakes. Consider a pond in wintertime. There's life in and around the pond, including fish and other aquatic animals in the water. As the temperature drops, ice forms. It forms on the top because that's where it's the coldest. If the ice were heavier than liquid water, it would sink to the bottom. As more ice formed on the surface, it would also sink, until eventually you have a solid block of ice. Of course, we know that's not what happens. Ice forms on the top and stays there. That layer of ice may get thicker during an extended cold spell, but it's still on top. That means the liquid water underneath it is still capable of supporting life. In fact, the ice on top acts as a layer of insulation, keeping the water from getting too cold. The illustration at right shows why ice floats, or why water is more dense as a liquid. Let's start on the right-hand side of the picture, which shows ice in its solid form. In the solid form, water forms a regular crystal lattice, and the hydrogen bonds between the molecules in this lattice hold them at a distance from one another. If you compare that to the liquid water at left, the water molecules are still interacting with each other via hydrogen bonds, but they're not fixed, and therefore the hydrogen bonds are breaking and reforming all the time. And on average, the water molecules are closer to one another in liquid water. That's what density is, how close the molecules are to one another. To recap, water is a very polar molecule, and its polar nature allows it to form extensive H bonds, giving rise to its four special properties: temperature moderation, cohesion and adhesion, water is the solvent of life, and water is denser as a liquid. These properties are necessary for life as we know it. When we look for life beyond Earth, therefore, we focus on finding water, especially in its liquid form. Earth is very special in its abundance of liquid water. Mars and Venus, our nearest planetary neighbors, are too cold or too hot for liquid water, respectively. The Kepler Space Telescope was specifically launched to find planets orbiting other stars, so-called exoplanets. It and other projects have identified thousands of exoplanets. Kepler 16b, fantasized in the poster at right, was the first planet discovered to be orbiting two stars and so would have two sunsets, like Luke Skywalker's Tatooine. Kepler 16b, however, is likely too cold to support life. It lies outside the Goldilocks zone or habitable zone, where temperatures are likely to allow liquid water. Many exoplanets have been identified in the habitable zone. Do they have liquid water? Do they support life? Maybe someday we'll know.